As human infrastructure expands rapidly outward, massive highways physically bisect ancient forests, creating permanent divisions in the landscape. This fragmentation disrupts complex biological systems. It cuts off natural migration routes, alters local water drainage, and isolates animal populations into unsustainable pockets. To manage this type of expansion, planners need a standardized way to predict and measure the exact toll of development on the natural world. That mechanism is Ecological Impact Assessment, or EcIA. It provides a scientifically defensible protocol for ecosystem management, turning the effort to protect nature into a measurable process. To accurately evaluate ecological damage, assessors pull data from 3 distinct scientific domains. This diagram maps the domains. Earth sciences account for the physical environment, including climate, air, water, and geology. Life sciences supply terrestrial and aquatic ecology data. Social sciences map human factors, from socio-economic impacts to cultural heritage. Their overlap creates a unified assessment protocol. Within this multidisciplinary structure, EcIA operates as the critical biological node. This framework forces specific adjustments across major development sectors. By identifying, quantifying, and evaluating how human actions affect ecosystems, the assessment requires concrete responses from developers. This chart maps those requirements. The process demands better predictive techniques and gives stakeholders a formalized role in project capacity. Moving around the diagram, it dictates institutional decisions, shifts corporate structures, and requires engineers to alter designs to accommodate the local environment. Embedding these ecological requirements into corporate structures and engineering designs forces development planning to align with specific biological limits. To function across all those sectors, the assessment relies on 8 governing principles. These rules mandate that all decisions are transparent, that decision-makers are held accountable to all parties, and that the assessment is conducted with scientific credibility. Simultaneously, the process is designed to be flexible enough to handle any project and cost-effective enough to ensure environmental protection at the least cost to society. This numbered list outlines the rigid 8-step life cycle that frames every ecological evaluation. The work begins with the initial project design, screening it for potential risks, and scoping the exact environmental boundaries required for the study. Then comes the operational phase, executing the actual impact assessment and evolving the project design to mitigate discovered damage. Finally, assessors identify residual impacts, submit official reports, and establish long-term monitoring plans. EcIA acts as a continuous feedback loop that starts at project conception and continues for years after construction is complete. Executing those 8 steps in the field requires a specific set of analytical tools. This list details the primary methodologies available, ranging from ad hoc checklists and matrices to complex spatial analyses and simulation modeling. The chosen tool depends on the availability of local data, the required data format, and the technological sophistication of the project. Whether using a rapid assessment technique or advanced GIS, the goal is the same: transforming raw environmental data into a structured impact profile. Once data is collected, it is categorized to reveal the project's systemic footprint. This diagram maps out the 3 environmental parameters used to categorize developmental impacts. The ecology parameter tracks direct damage to terrestrial and aquatic life, measuring threats to species diversity and endangered habitats. The physicochemical parameter accounts for changes in water quality and soil characteristics, while human interest covers socio-economic impacts like land loss and landscape aesthetics. A single construction event rarely remains isolated. Disruptions typically bleed across all 3 parameters simultaneously. Consider how these parameters map onto linear infrastructure, like a major highway. In terms of physicochemical impacts, road embankments alter the local topography. If built across floodplains, they can create a backwater effect, increasing the frequency of flooding upstream. Roads also interfere with cross-drainage and cause heavy siltation in downstream water bodies. In the ecological parameter, highways often encroach upon and destroy sensitive wetland habitats. Runoff from the road can lead to eutrophication, where nutrient overload causes algae blooms that suffocate aquatic life. Within the human interest parameter, thousands of acres of agricultural land are often permanently lost to construction. However, this parameter also captures positive impacts, measuring the generation of employment and the opening of new trade corridors. Modern rail networks face similar multi-parameter disruptions. These projects require topographical alteration, rock blasting through natural formations, and introduce persistent noise disruption into previously quiet areas. Linear infrastructure triggers an interconnected cascade of effects across the region, requiring precise calculation to determine the long-term viability of the project. Listing positive and negative observations in a report is insufficient for engineering and policy design. Planners must quantify those qualitative field observations into a mathematical score. This is achieved through the environmental impact value calculation formula. The V variable represents the relative change in environmental quality caused by the project. The Y variable measures the ecological weight, or importance, of that specific parameter to the surrounding region. By multiplying magnitude against importance, the formula prevents minor changes in critical habitats from being mathematically ignored by developers. The sum of these individual calculations provides an objective, standardized scoring scale. Projects are graded on a scale from 0, meaning no environmental change, up to 5, indicating severe systemic impact. High-speed rail projects use these scores to balance their ecological disruption against their economic and transport benefits. The ultimate purpose of this math is to make nature readable and actionable to civil engineers and policymakers. By translating qualitative ecological data into a rigorous mathematical framework, EcIA allows biological preservation to function as a concrete variable in